about density and center of mass. So if you've had some physics, some of this stuff at the beginning is going to be like, yep, I know that. Density is the concentration of mass in an object, like how much stuff you can fit into the space of an object, how much stuff there is. And it's usually measured in units of mass per volume, like how many grams per centimeter, per cubic centimeter, right? And you can kind of tell density by, well, it's a different thing, but it's by weight. Like if you have a really small thing that's really, really heavy, you know, that is dense. There's a lot of stuff in a small object. I also think about it in terms of like cake, like a really dense chocolate flourless cake is like, you can only eat a few bites of it because there's so much stuff in that one little piece of cake, versus like angel food cake that's mostly air, right? So an object that has uniform density, so the density is the same throughout the whole object, satisfies the basic relationship that the mass of the object can be calculated by doing the volume times the density, right? Because your units on volume would be something like centimeters cubed, right? Cubic centimeters for volume. And then your units for density would be something like grams per cubic centimeter. Your cubic centimeters cancel, and you'd be left with grams, a measurement of mass. All right, and you can also use density for 1- and 2-dimensional objects. So if for a 1-dimensional object, we would measure mass by distance times density. Instead of volume, use distance. Or for a 2-dimensional object, instead of volume, use area. Area times density. But when the density of an object varies, it's not the same everywhere, those basic formulas no longer hold. You can't just apply a simple formula if the density isn't the same throughout the entire object. So we have to use calculus to calculate total mass. And to do it, you slice the object up in such a way that each slice has approximately uniform density. Apply the easy formula on each slice, and then add all the slices up. Once we let the number of slices go to infinity, that would be an integral. So here's an example. We have an open cylindrical barrel. You guys can grab some notes right there. We have an open cylindrical barrel that's diameter 7 feet, height 21 feet, and it's filled to a depth of 10 feet with muddy water. So I'm just going to draw a quick picture. Cylindrical barrel. It's got diameter 7 feet. And it's filled to a height of 10 feet with muddy water. So this is muddy water in my barrel. Okay, but the density of the mud in the water is not uniform throughout the whole thing. If we took a big stir and stirred it up, it would be uniform for like maybe a minute, right? And then the mud tends to settle at the bottom. So we're going to say the density, it's going to vary linearly. The density of the water, mud in the water, will vary linearly with the depth of the water. So it'll be most dense at the bottom, most mud is at the bottom, and then less dense as you go towards the top. So we're going to say the density at the bottom is 80 pounds of mud per cubic foot, and the density at the top will be 30 pounds of mud per cubic foot. And we want to find the total weight of the muddy water in the cylindrical barrel. So first we need to come up with a formula, a function that measures the density of the mud at any given point. Any ideas? Yeah, how'd you get that? Y-intercept, yeah. So we say we've got points. We've got like 0, 80, and then what's the other point? 10, 30. Yeah. So it varies linearly, so we could just make a line that involves these 2 points. And we're thinking this as 0 and this as 10. Right? Think of this as like a vertical line there. Okay, so I have 2 points. Each of these points represents, position, an x value for position, and then the y value is the density. So if I find an equation for this line, it would be something like, we'll call this delta of x. And that's a delta it's often used for density. Okay, so it's a Greek letter delta, lowercase delta. Rho, we use that too. Yeah, so I'm going to use that in the next one. Yeah. Okay, so delta of x will be the equation of this line, which you told me was what? Negative 5x plus 80. Just the equation of the line that goes through those 2 points. So at any given point in the barrel of muddy water, I can calculate the density of the water at that point. All right, so what I'm going to do is I'm going to calculate my weight, right, in pounds of one random slice. I'm going to pick one slice, maybe like right here. It's a terrible picture. Okay, so one little slice of the water. Imagine that if you could just like pick it up and you just have this little round slice of muddy water. I know its density, or I can calculate its density using this formula, and I can calculate its total mass by doing density times volume, right? Okay, so for my slice, I would like to know the mass of my slice, and I do that by doing density times volume. Okay, so my slice is going to be at a random height from the bottom, x. Distance from the bottom. And I'm going to make it so thin, this is going to have such thickness that delta x is going to be so small that I can assume the density on the whole slice is practically uniform. It's going to be basically the same because it's so thin. So I can get the density from my formula, and the volume, that's just a disk, and the volume of a disk is just going to be pi r squared delta x, right? Okay, so my density is given by this formula, negative 5x plus 80. And then the volume of that disk would be pi times, what's the radius of that disk? 3.5, because that radius is constant, times delta x. So that's the mass of a single slice. Mass of a single slice, because the density is given in pounds per cubic foot. The mass, the volume is measured in cubic feet. So when I multiply these together, I should get pounds. So doing a unit analysis on these word problems can be really handy because it really verifies why you're multiplying these two things together. Okay, so density is negative 5x plus 80. That's measured in pounds per cubic foot. Volume is measured in cubic feet. Cubic feet cancel, and my units will end up in pounds, which is what I was trying to find. How many pounds of muddy water is in this cylinder? Well, I can figure out how many pounds a random slice is, and then I'm just going to add up all these slices and let the number of slices go to infinity. So I think I need a new slide. The number of slices is going to go to infinity, but I'm gonna stack those slices up from 0 to 10. Okay, so I'm going to add up all my slices, and each one has mass. So my total mass is going to be the sum of the mass of all my slices, and each one has mass -5 xi plus 80 times volume, which is 3.5 pi 3.5 squared delta x. Okay. So my mass is just going to be a sum of all these slices, right? Each slice is at some height x sub I. So when you take I going from 1 to n, right? So you're going to use n slices, and then I let n go to infinity, this sum becomes what? Yep, the limit as n goes to infinity of a sum becomes what mathematical object that we've been studying all semester? An integral, thank you. So the exact mass is going to be the integral from 0 to 10, because those are my bounds where I'm stacking up these slices, of -5x plus 80 times 3.5 squared pi, and the delta x becomes a dx when you take the limit. Okay, because as you let the number of slices go to infinity, the width or the thickness of each slice, which is delta x, when we let the number of slices go to infinity, that width gets really, really, really small, and we call it a dx when we do the limit. Okay, so this isn't that hard of a problem, right? We can solve this integral. So maybe we'll just simplify it a little bit. I can take my 3.5 squared pi right out of the integral because it's just a constant. Okay, so this becomes 3.5 squared pi times the antiderivative of -5x would be -5x squared over 2. Antiderivative of 80 is 80x. Okay, so when I plug in a 10, 10 squared is 100, -500 over 2 is -250, plus 800. 550? I think it's 550. Yes, 550. 550. And when I plug in a 0, I get 0. So let me open up a calculator. .5 squared is 12.25 times 550, which is 6,737.5 pi, or approximately 21,166.4805 pounds of muddy water. It is a lot, but it was 10 feet, right? A 10-foot barrel is really big, 7-foot diameter. That's huge. So does that kind of make sense? If you know something about the density, to get the mass of a single slice, you can just multiply your density times the volume of your slice, and then add up all your slices, and you get an integral. Should we do another one? Okay, so we've got the density of oil in a circular oil slick on the surface of the ocean. So there's some kind of oil spill, right? And the density at the center of the oil spill would be the greatest, and the density gets less as you get further and further away from the site of the spill. So the density is given, R meters from the center of the slick is given by this formula, rho of R, where R is the radius away, right? So rho is another common Greek letter used to represent density. So that would be 50 over 1 plus R kilograms per square meter. And this time we're dealing with square meters instead of, which is a measure of area, because an oil slick covers area and the thickness is not as important to think about. Okay, so if the slick extends from R equals 0, the site of the spill, to R equals 10,000 meters out, we want to find the total amount of oil in the slick. Okay, so let's draw a picture. Here's my oil slick. We're assuming it's a perfect circle, right? Because even if it's not, this would give us a pretty decent estimate of the amount of oil that has spilled. Okay, so my density varies as I head away from the center of the spill. So what I'm going to do, my slices where density is approximately the same are going to look like what? How am I going to slice this thing so that on each slice density is approximately uniform? Pie slices? So the density on this slice is the same all the way out? Concentric circles, yeah. Yeah, so if I make a little concentric circle like right here, very, very thin thickness all along this little ring, the density would be approximately the same because all around here is approximately the same distance from the center of the spill. Okay, so I need to know the density at this distance away. So we'll call this distance away R sub I or something. We'll call this, or maybe we'll just call it X. No, we'll call it R. R sub I, right? And then we'll call the thickness of the ring delta R. So I need to know the density at R sub I, which I know from the formula, right? That was given to me. And I need to know the area of that ring, how much area that is. Okay, so remember that amount of oil in kilograms. So the mass of my ring, or my slice, however you want to call this, is density times area, right? Because density is being measured in kilograms per square meter. Area is being measured in square meters. So this will end up being kilograms, a mass. Okay, so my density at this particular radius at R sub I, some random R sub I, is going to be 50 over 1 plus R sub I. So there's my density. And then the trickier part of this problem is figuring out the area of that ring that has some small thickness. Right? I need to figure out the area of that ring. Any ideas? Pi R sub I. Oh, okay, so find the volume, the area of the outer circle, subtract the area of the inner circle. You could, but it gets very messy. Yeah, it gets very messy. We're going to do something a little bit trickier, a little slicker, if you will. All right, so I'll give you one little hint. Imagine that you could take a pair of scissors and cut this circle and unwind it, right? And lay it as a long, straight thing. What would it look like? A rectangle. And what would the height of that rectangle be? Delta R. And what would the length of the rectangle be? The circumference of the circle. Yeah. And it might feel like, well, that's not really quite, I mean, you're doing, like, which circumference should I use, the inner or the outer, right? Whichever one I choose, it's not going to be really correct. But when I let the number of circles go to infinity, that delta R is going to go to 0, and it'll all work out perfectly. Okay. So my area is going to be the circumference of the circle at R sub I, which the circumference of the circle is 2 pi r, right? So this is going to be 2 pi r sub I. That's the circumference of the circle times the width of the circle, because that would be the height of a rectangle, delta R. So then I'm going to have a whole bunch of these concentric circles. One here at a different R sub I. This might be like R sub 4, right? And then I've got one out here at a different R sub I. That might be like R sub 8 or something. And I want to add up the masses of all these circles. So I'm going to take a sum where I add up the masses of all my rings. So my mass total will be approximately the sum of n concentric rings. And each one will have a mass given by this formula. 50 over 1 plus r sub I times 2 pi r sub I delta R. Okay. And then I let the number of slices, the number of concentric rings, go to infinity, which means that the width of those rings goes to 0, and I'm going to get an integral, so that my mass will be equal to an integral. I take the limit as n goes to infinity, that becomes an integral. The r sub i's just become regular old r's. So I have 100 pi r over 1 plus r, just multiplying those two together, like over 1, dr. And what are my bounds of integration? From where to where am I stacking these concentric rings? 0 to 10,000. Okay, so doing this particular integral by hand, I don't really want to. So I'm just going to have my calculator do it. Okay, so I hit math 9, put in my function 100 pi x. I should maybe have parentheses around that. Divided by 1 plus x, comma x, comma 0, comma 10,000. Okay, there we go. So 3,138,699, and we'll just round it to there. What are my units on this? Kilograms. Kilograms of oil in the oil spill. All right, I think you should try one before we move on to another topic. So I'm going to have you turn to oh, shoot. I don't think I have one. Never mind. You can try it in your homework. All right, so we'll skip over the challenge for now. We're going to talk about a seesaw. We're going to talk about moving on to center of mass here. So the center of mass of an object. So now we've spent some time figuring out how to find the mass of an object. If you know something about its density and its length or area or volume, you can find its mass. And now we want to talk about where its center of mass is. And the center of mass of an object is that object's balancing point. So if you have a 75 kilogram father and a 25 kilogram daughter sitting on opposite ends of a seesaw that has length 8, if you neglect the mass of the seesaw, where should the father sit so that the seesaw balances? You don't have to do any math, like in general, like don't give me a number, but where does he have to sit? Closer to the balancing point, right? So the father and the daughter have to sit, right? If you put, here's my balancing point, which we can't move because seesaw, it's like screwed into the seesaw, right? So if you put the daughter here, then the father would have to has to sit closer, right? And the question is, exactly where does he have to sit? Does anybody know? Happen to know because you took a class in physics? He's going to move in because we can't move the center point. It's like bolted to the seesaw. Nothing yet? Okay. So the answer we end up finding by using something called the moment. The moment of a mass is a measure of that mass's tendency to swivel the seesaw about the pivot point. Okay. So the definition, the moment of mass about the pivot point is equal to mass times displacement from the pivot. Okay, so if the pivot happens to be at the center of mass, the sum of all the moments that make up the mass of the system has to be 0. And we denote the center of mass by x bar. So here's how we find the center of mass for the father-daughter example. So I have 2 pictures here because I'm going to solve this 2 different ways. In this one, we can move the pivot so that we can build a seesaw where we put the pivot in a place where the father and daughter will balance. But in this one, we're at like a playground where you can't move the pivot because it's bolted to the seesaw, and we want to figure out where the father should sit. Okay, but you use the same concept either way, you're solving for a different variable. Okay, so moment, remember, a moment is mass times displacement from the pivot. Okay, so in this first example, we're putting the pivot at some unknown location, x bar. Okay. So we've got the daughter, so my moment for the system is mass times displacement, the sum of all the masses times their displacement from the pivot, and we want that pivot to be the center of mass, which means that the sum of the moments has to be 0. Okay, so the daughter is 25. Her displacement from the center of mass is x bar, but she's to the left of the center of mass. We call that negative. And then the father, his mass is 75, and his displacement from the pivot is, well, in our example, it was 8, right? The full length of the seesaw was 8 minus x bar. And that has to be 0 in order for x bar to be the center of mass. The pivot has to be the place where the moments add up to 0. So I just solve this equation. Negative 25 x bar plus 75 times 8 is 600, I think, minus 75 x bar equals 0. And you get x bar has to be 6. So that means that this is 6. The distance from the daughter to the pivot would be 6. And then from the pivot to the father would be 2. What is the common relationship between 25 and 75 and 2 and 6? 3 times. Yep. Yep. So the father weighs 3 times as much as the daughter, so the daughter has to sit 3 times as far away from the pivot. Okay, similar problem. In fact, almost the exact same problem, but this time we can't move the pivot. Pivot is where it is, so all we can move is the father. Okay, so in this case, instead of putting the father on the end, we have to move him closer to the pivot, and we need to figure out what this distance needs to be to make it balance. So we do the same thing. We add up the moments. So the daughter, her displacement from the pivot is -4, because if the whole thing has a length of 8 and the pivot's in the middle, she's 4 feet away. So the moment would be 25 mass times a displacement of -4. And then the father's moment would be 75 times a displacement of L minus 4. Right, so in this case, we need to figure out what L is, because we're not using the full 8 feet. Right, the father's not going to sit at the end. And we need that to be 0. Okay, we know x bar. We know x bar. The center of mass has to be at 4, because that's where the pivot is. So this time we just solve for the length of the whole seesaw. So we get -100 plus 75L minus 150 equals 0. Sorry, 300. I can multiply in my head. 75 times 4 is 300. Okay. So I get 75L equals 400, and L has to be, I think it's 5 1/3. So the length of the whole system has to be 5 1/3, which means that the father has to sit 1 1/3 feet, or whatever my units are, from the pivot. Yeah? Mm-hmm. Hmm. Yeah, that's equivalent to saying adding the moments together equals 0, is that the moments on each side have to equal each other. Does that make sense? Yeah. Yeah, so that is an equivalent way. And yes, this seems like a lot, but have we done any calculus yet? No. So we're building towards doing this when we have non-discrete weights, and we have to add, you'll see. So the process works the same if you have n masses, instead of just 2, 1 on each end, right? If you have n point masses at positions x1, x2, xn along this balancing thing on the x-axis, then this is how you find the center of mass x bar. You add up all the moments, displacement times mass. And when you do that, you just distribute and simplify, you end up with this sum, right? So if x bar is my center of mass, so let's draw a picture. We'll call this x bar. This is which I don't know where it is. And I have all these point masses, one at x1, one at x2, one at x3, a whole bunch of them. Oops. And then x whatever, n-1, x sub n, right? So my moments have to all add up to 0. So I have to take each point's displacement from the pivot, add them all up, multiply by the mass, add them all up, and that will give me x bar, right? So my moment for x1 would be its mass m1 times its displacement from the pivot, which would be x1 minus x bar. And then I would do the same thing for the next mass, the next point. I would have m2 times x2 minus x bar plus blah, blah, blah. And I would do this for every point on my seesaw. mn times xn minus x bar, and this all has to add up to 0. And when you solve this thing for x bar, you have to distribute your masses, right? And you're going to have m1 times x1, m2 times x2, mn times xn. That's the numerator of this thing. That's the sum of the xi's times the mi's. And then you're going to multiply your masses times your x bars. So you have m1 times x bar, m2 times x bar, up to mn times x bar. And when you solve for the x bar, you're going to have to divide by those coefficients, the m1 plus m2 plus m3. I'll show you. m1 x1 plus m2 x2. Right, so that's what you get when you distribute the m's to the first term in parentheses. And when you distribute to the other term in parentheses, it's going to be negative, and I'm going to add it to the other side. So I'm going to have m1 x bar factor out the x bar, divide both sides by the sum of m1 to mn, and that's what this denominator is. So that is my formula for finding the center of mass when you have more than 2 point masses. So let's just use that formula for the father-daughter example on the 8-foot-long seesaw. So we're going to verify the center of mass. We already figured out it should be at 6, right? In the case where we can move the pivot, it should be at 6. Okay, so I want to use my formula, x bar equals the sum of xi mi over the sum of the mi's. And this should give me 6 because I already calculated it. Okay, so the sum of the xi mi's, that means for every point on my seesaw, I have to add the distance it is, its location times its mass. So the daughter is at one end, right? So she's at -4, and her mass is 25. And then the father is at the opposite end, 4, and his mass is 75. So location is the xi times the mass, divided by the sum of the masses, 25 plus 75. Okay, so 4 times 75 is, I think that has to be a positive 4. Yeah, because it's not, no, because they're going to sit on opposite ends of an 8-foot. Oh, maybe it's 0. It's 0 and 8. That's what it is. Yeah, thank you. We're going to let one end of the seesaw be 0 and the other end be 8. So 0 and 8. So, or, yeah, that's fine. So that ends up being 600 over 100, which is 6. That's what we got before. Mm-hmm. Right. Yeah. Okay, so the question is, though, what if the masses on your seesaw aren't discrete, right? But instead you just have one object, like it's just one seesaw, one long plank, but it has varying densities along this one plank. How would you compute its center of mass? So here's my object lying on the x-axis from A to B. So I would let delta of x be the density at point x. So think of this rectangular object thing here as a seesaw, and it has density varying along its length, given by this formula, some random formula we don't know, delta of x. Okay, so the mass of a typical slice, right? If you pick a random slice x sub I, its location is x sub I, and its mass would be its density times its length, right? When you're dealing in just 2 dimensions, you just do mass is density times length. So here's its mass, and here's its location x sub I. So my summation formula becomes the sum of mi xi over the sum of the mi's. It's the formula we were just using. But then my mi's translate to this formula. So I get the sum of delta of x sub I delta x divided by the sum of the mi's. Oh, sorry, and the mi's are, I need an xi here. There we go. So the xi is position, the delta xi delta x is the mass over the sum of the masses. And then we let the number of slices go to infinity, and you get an integral. So we end up finding the center of mass x bar by doing the integral from a to b of x delta of x dx divided by the integral from a to b of delta of x dx. So deriving the formula is a lot more complicated than using it. Let's say you have a 2-meter long rod. It has a density, x units from the end, of 5 plus x squared kilograms per meter. We want to find its center of mass. So I've got this 2-meter long rod. Pick a random spot, x sub I, right? Its density at that spot is 5 plus x squared kilograms per meter. So I just can use this formula. X bar is going to be my integral from 0 to 2, because it's a 2-meter long rod, of x times delta of x divided by the integral from 0 to 2 of 5 plus x squared dx. This is a sum of the moments, position times, no it's not, sorry. This is the sum of position times density. And this is just the sum of the densities. So I get 5x squared over 2 plus x cubed over 3, evaluated from 0 to 2, divided by 5x, oops. Distribute that x and you get an x cubed, so that becomes an x to the 4th over 4. Okay, so if I plug a 2 in here, 2 squared is 4, times 5 is 20, over 2 is 10, plus 2 to the 4th is 16, over 4 is 4, so I have 14 minus 0 over When I plug a 2 down here, I get 10 plus 8/3 minus 0. (21/19), which is approximately 1.105. So there is my center of mass. The balancing point for this 2-meter long rod is just a little bit past the halfway point. So we have analogous formulas for finding the center of mass of a 2- and 3-dimensional region. You can find them in your textbook. I think I might have given you like one homework problem about a 2-dimensional region. I won't put any of these on a test because I didn't cover them in class. All right, so now I want you to work on this activity, a penny saved.